Okay, so I decided to make a quick video on basically how to reset the Pioneer TTC-200, which you would have to do in the event that you ever moved it or recalibrated it, or like me, you crashed your machine like I did into my vise and your Z-axis encoder is shifted slightly, so that pretty much, you know, cancels everything that you put into the computer, from your tool lengths to your probe location and stuff like that. So thought I'd do a quick video. It's going to be broken apart and poorly assembled like always, but hopefully it'll help someone. So the best way to do this is to create a master tool. So I've just used this ER32 collet holder. So by the way, if you're ordering this machine or a machine this size, ER32 is too big for most of the stuff you're probably going to do, so I've got a bunch of these left over, so I didn't mind burning up a ER32 holder for this. That is a broken 1/4-inch carbide end mill that's stuck in backwards, and I tested the run out, and at the tip it's 3/10. So I mean, you probably want better than that, but that's all I've got, so that's what I'm going to run with. And I'm thinking about it, so that's 3/10 as it rotates. Let's say its diameter is, 0.25 inches. As it rotates around with 3/10 run out, I think that means that the diameter as it's spinning is about 1.5 too large. So I'm interested to try that out as a theory when I measure it when I'm done, and see if that's true. Because it's not going to care about the wobble in, it's only going to care about the wobble out from its true diameter, which I think is only half of the total indicated runout. So, yeah, basically the first thing you want to do is set up an indicator on your machine, which I'll do. Excuse the mess. So, with your indicator installed, you want to jog the probe tip over to your I don't know, I just roughly tried to center it on the, sorry, this is not going very well. Centered it on the tool diameter roughly, which, I don't know, that's pretty close. That's going to move over a tiny bit. Take a positive. So, and then you just jog down in Z. And that was too much. So, you just arbitrarily set a 0 point on the indicator, and we'll slowly work up to that. There we go. Sorry, I'm trying to watch, not video. So, basically, there. So what I would do is, in the controller, use relative mode, and you can zero out Z. So basically this just establishes a reference point for the end of the tool. So we will go up in Z now, and we're going to pull that out of the spindle, which I can't do without my hands. Hold on. You can sit there for a second. So now, with the tool out of the spindle, now jog down again. And we're going to measure the spindle nose. And so y minus, well, y plus x. And I just have to pick in between these screw holes over here. So we're going to line it up just right about there. Come further down in Z. call that good. Sorry, I know this video is absolutely terrible. I'm just trying to hit a spot that's, you know, not got a screw hole in it. Pretty straightforward. So then jog down. And now we're going to jog this down, oops, until it's 0 on the indicator again, which we haven't moved. There. And then you come over and read this number, 86936. So that's interesting. So this is the number I got doing this last time, 86.933. So it's 0.003 different, but it just could be the location I picked on the spindle to do it. But that right there is now the length offset for your master tool that you're going to use to then set the location of this guy. So I'm going to stop this video and then set up to do that test, that calibration, and run it. Alright, so I will be right back. Okay, so now we've got the machine jogged over to roughly the center of the stylus of the probe. It's within about a centimeter above, which they kind of call for in the routine. So in Machine Data Automatic, you enter in this routine which calibrates basically the location of the top of the probe, the electrical top of the probe. So L960, that clears all the previous R values or that are set in the system. R0 equals 86.9333, so that is the length we measured for our what they call the standard mandrel. So that's your master tool. And then L967 is this measuring cycle that will set the top of the probe. So I'll run it again here. I did just obviously do it just now as a test, but we'll run it again just so you can see it. So 1 hit, 2 hits, and I got the feed rate at 50%. I'm not sure how big of a difference that'll make, but the last measuring is very slow. So I'm assuming it averages between all three, and that's it. So that's set. So now the next thing we need to do is calibrate the diameter of the probe. So that is to find the center of it. So I'll reprogram that and get set up again, and then we'll do that one. Okay, so now we're set up to do the diameter location calibration, and basically you set the probe above the center of it. You tell it roughly how high it is above the center of the stylus. So L960 clears all the previous variables. R0 is the probe diameter. R3 is the mandrel diameter. R2 is the height from the bottom of the tool to the middle of the probe. And then L968 is the routine to measure the diameter. Of course, M30 is in the program. So I'm going to let this run just so you can see what this looks like. I obviously just did it so I didn't scare myself. I'm still going to dial the feed rate down because I'm a little nervous. So we'll do 70%. So it does X first on both sides. And then it'll do Y. This will be it. We'll return to center. So now that's done and it's set. So the next thing we can do is actually measure some tools. I'd actually like to measure this standard mandrel and just see what it comes out with for fun. So I'll do that next. Okay, so now we're ready to actually try and measure the master tool just to get an idea of how things were set up. So I would expect we should be able to measure that tool and have it be pretty repeatable to what we used to set it up. So, excuse me, hold on. Excuse me. This is the edges. So for those of you that don't know Siemens, you can have more than one cutting edge for the same tool number. So you can have more than 12 tools in the controller. So tool 12 D1 is this, which is, I think it's a drill, I forget. And tool 12 D2 is our standard tool. So that 86.933, that's what I measured it to when I originally used the indicator to measure it from the spindle face. And this is the radius. Now, that's just measuring it with calipers. Obviously that's not super accurate, but remember I said it was running about 3/10 run out when I measured it. And I speculated that that might cause the effective radius to show larger than it really is. So I'm kind of interested to see how that turns out. And then I've got another thought too about, you know, when you're running the calibration routine, I'm wondering if a person shouldn't actually have the spindle rotating, even though it doesn't do it automatically. I'm thinking it might be a good idea. But anyway, we'll run it and see what happens. And this is the routine to do it. 960 clears all the variables. R7 equals 3, it's going to test the length and the diameter. R1 equals 12.2, so this is the cutting edges thing again. So that's tool 12 D2, so that's the second position in tool 12. Yes, that can get confusing. I like it, so I don't mind it, but I can see that a lot of people might not like how that works, but I'm just glad I can put more than 12 tools in there. R3 equals 3.155, that is the diameter that I measured with calipers. L969 is the actual routine to measure the length and diameter. M30 is in the program. So we're going to run it and see what we come up with in our offset table. And then I'm going to switch it back to what I measured it to. I think that I'm not going to let it do that automatically. I'm not sure. I got to think about that again. But I think I'll want to leave that as the manual values I came up with, except for the diameter. I'll show you in a minute. So we're going to run it. Okay, so it's completed its program. We'll look at the offset table. So 86.935. So that's indicating 0.002 millimeters different than we measured with our indicator. So that's pretty darn close. I don't know what that would be in inches. And then the radius, so this is the more interesting part. So it's 0.01 bigger than I measured it to, and I think that that's probably to do with the runout. So I'm going to do some math and figure out what So it's 3 thou run out. Like I said, I think that'll make the tool run about 1.5 thou too larger than its real diameter. And I think that's going to come out to be pretty close to what we're measuring for it being too large. So I'm going to do the math on that, and then I'll probably show you guys what I calculated it. And if that's true, I may want to set this as the actual radius and diameter of the tool and run the diameter calibration again with the spindle running. I think that would ultimately yield a way better result. So I'll have to wrap my head around that more and maybe give it a try and just see how it works out. But so far I'm happy with how this is turning out. This is the first time I've done it myself. Obviously it came done from the factory, but I crashed the machine, so I had to reset everything. But I'm kind of glad I have had to, because it's forced me to figure it out. And I set up the probe a little better than they did. I think there was about, I forget, it was probably close to 1,000th of deviation, like non-flatness in X and Y on the probe, and I got that down. I think in X it's like 0, and in Y there's maybe 1 or half a tenth of deviation. So I'm happy, and now I know I can trust it. So I'm going to do this math and see if I can trust this too. Hold on. Okay, so I went through the math. First of all, on the length, it turned out we were 0.002 millimeters off what we measured with the indicator, which turns out it's like 0.8 10,000ths, or I guess 8 100,000ths. So I'm not really worried about that. I'm not going to try and figure out what's going on there. That's a very small number that I'm extremely happy with. Onto the diameter. So I did the math, like I said. It turned out we were 0.02 millimeters off, which is about 7.7 tenths off, 7 100,000ths, or wait, no, that's 7 tenths. We're about 7 tenths off, 8 tenths if we round up. So and I recalled there was about 3 thou run out. So when I did the math, I thought what it should have measured is 6.3176. So that was still considerably off what we measured on the machine. So I decided to test it again. So I put the indicator back on it, and I was a little more critical of it, and it's about 4.5 tenths. So I've redone the math for 4.5 tenths, and I come up with an effective diameter of 3.2143. So the next thing I'm going to try and do is see if I can run the tool probe calibration diameter program with the spindle running. See if I can turn the spindle on and then run the program and see if it keeps it on or not. There's a good chance it might obviously turn it off inside the program, but I'm going to give it a try and see what happens, because I feel like, it would be nice to be able to do that. I'm pretty surprised you can't. So even if I had to go in and try and modify their macro, I think it should spin, is the bottom line. If you had a tool that had no run out, like Meritool sells those probe calibration things. I mean, I'm not sure that it would read 0 on my machine. Like, I'm assuming there's a tiny bit of run out in the spindle. I guess maybe not on like a D&G or something like that, but I feel like there's a chance there'd be something, even if it's like half a tenth or something, and I would think you'd want to be able to compensate for that. So anyway, I'm going to mess around with it, and I will see what I can come up with. Okay, bear with me here. So my diameter I was using when I measured the tool, 6.31, turns out that was wrong, and it makes sense that it's wrong. I mean, it's a carbide tool blank, so you'd imagine it's going to measure pretty close to the real deal, which would be 6.35. I measured it again. It is 6.35. we went through the runout together. So that runout, if you think about it, so if the diameter is 6.35 and it's running 3/10 runout, that's 1.5 larger at every revolution on this side and on that side. So you effectively actually get an effective diameter that is the amount of the runout, I believe. And if that's true, I can add 0.01143 to the diameter I measured on the bench because of the runout. And when I measure the tool now on the probe, so I redid the calibration using 6.35. So that's going to be a bit of a mixed bag depending on, you know, what edge of the tool it's testing on which side of the probe because of that little bit of runout, so it's not going to be exactly accurate. But when I measured it, I got a diameter of 6.366, and I calculate that the effective diameter of the master tool would be 6.36143 because it's spinning around its true center. And I mean, if that's true, it's 0.005 off the 0.005 off of the diameter. So that means it's essentially about accurate to about 2/10 right now is what I am feeling. So I'm gonna run some test cuts later, not today, I'm running out of time, but I'm pretty happy with that. I'm pretty happy I was able to wrap my head around it. And I mean, someone might correct me about my logic, but this was the result of the test I just did. Length is a little bit off from what we were measuring previously, but I'll look into that more. Anyway, 3.183 is what I just came out with for a radius, which is, like I said, 6.366. So, anyway, I hope this video helps someone other than myself, and I think that's it. Alright, talk to you later. Okay, one more update. I noticed the length was a little bit off after doing the other calibrations, so I decided to rerun all the calibration cycles with the actual diameters that are refined now, and I ended up getting the length back to 86,935, so again that's 0.002 off of what we measured with the indicator, which is next to nothing, like literally next to nothing. And I ran the diameter again, and now it's so I'm not cheating on the actual calibration. I'm using 12.7, which is the calibrated diameter of the stylus, and I'm still using 6.35 because it's not rotating. So, you know, there's some fudge in there about where it's touching as opposed to where it's sitting in its elliptical path around the spindle. But the radius 3.181, so when you multiply that by 2, you get 3.362, and I calculated when it's rotating the diameter should be 3.3614. So it's a difference of basically it's half a tenth. So obviously I'm very happy with that. I'm very excited to actually put this to the test now and measure some tools, do some test cuts, and see how it compares. I mean, it would be amazing to be able to trust the probe to do the diameter of the tools so that you can do you know, in controller compensation for contour paths to make deadly accurate parts. So I'm pretty excited to give it a try. I'll let you know how I make out.